How about the other one? 2. That's a pretty big difference, right?
Yes.
Okay, what do you expect the multiplicities to be for the signals here? Just go left to right, I mean, or right to left, it doesn't really matter. 3, 2, 2, 3, agree? Yes?
I can't find my NMR sheet.
Well, you need to look for it. What about integration there? 3, 2? Everybody okay? Okay. What about multiplicities? So let's talk about the multiplicities. Meaning splitting. So what do you expect for the multiplicity for that signal to be? Triplet, everybody? What about this one?
Sextant.
Because there are 3 and 2, 5, so 5 plus 1, right? And what about these two? And what about this guy?
Single.
So there will be a singlet for 3 hydrogens. About where? Where should this be? Where do we expect this signal to show up?
Like one.
Not this one. It's attached to an oxygen. It's CH3 attached to an oxygen. Where are they expected to be? 3.5 ppms. Right. You expect a singlet to be around there. What about this triplet? Where do you expect this triplet to be, which will be pretty prominent as well? Say that again? Actually, not 3.3, 3.7. CH2 is higher than CH3.
Yeah,
Higher.
so it would be 3.7.
About 3.7. So we, if you're looking at the proton spectrum for this ether, we will definitely see 4 signals integration. But also, in addition to that, there will be a singlet at 3.5 and a triplet around 3.7, which will definitely be this guy. We good, everybody?
Yeah.
What about here? Only 2 signals, integration 3:2. Will there be a singlet at 3.5? There will be no singlet at about 3.5 because there is no CH3 attached to the O. You guys see that?
Yeah.
Where would these be expected? Careful. 3 so not 3.5, about 3.7 ppm. You'll see, what is it? What's the multiplicity for that signal? What do
Quadruplet?
Quartet. Quartet, so we will see a quartet at around 3.7, but no singlet. So what we are doing here, guys, is we are looking at the structures of the 2 compounds and trying to find the differences between them so that we can then say, okay, that will help us identify which compound the spectra belongs to. Make sense, everyone? Yeah? Okay, then what about the next one? Let's do number 2. So once again, you're looking at all the different things. Number of signals, multiplicities, integration, sometimes chemical shift also. So how do you think we will be able to differentiate between this compound and this compound using proton NMR? Please. What do you think? Let's start with number of signals. They both have 3 because there's symmetry in both, right?
Yeah.
Actually, this doesn't have 3. Yeah, it has 2 symmetry. It has a plane of symmetry here and a plane of symmetry there. So yes, absolutely, not 3. It has only 2 signals. And what about that one?
Wouldn't it be free signal?
That has only 1 plane of symmetry right there, so 1, 2, 3, exactly, 3 signals. Everybody okay? Yes? Does everybody agree?
Yes. Yeah.
Question, Vincent? No? Okay. What about the integrations for those 2 signals? What do we expect for the integration to be?
2 to 1.
excuse me, did you say 2 to 1?
Yeah.
Because let's say that is A, B, 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 not R, B. Everybody agrees?
Yes.
Everybody?
Yep.
Oh, wait,
No, four-
wait, not 2 to 1.
No, you're
Careful, careful.
Or 4 to 4.
2 to 2 or 1 to 1. Am I right?
Yep.
Did I do that correctly? Yes? Yeah, because there are 2 here and 2 there. If you're looking at this.
Oh, that's right. There's 2 hydrogens on the top.
Yeah.
Yeah, there are 2
Yeah,
B's.
yeah,
There
yeah.
are 2 B's on the top. 2
Be
B's on the
careful.
bottom, and one on the
Careful.
Good point, good point.
Yes.
One on the bottom.
What about the integration here?
2 to 1 to 1.
2 to 1 to 1 or 1 to 1 to 2, whichever way you go, absolutely. Everybody okay?
Yep.
What about multiplicities? Actually, that alone is pretty good to differentiate between the 2 compound. You got only 2 signals about equal integration. You got 3 signals with that integration alone. We'll be able to say whether it's this or that, right? Everybody okay?
Yep.
So that's kind of what we are doing in these examples. I'm not going to go through all of them, but that's kind of what we are doing in this question is we are looking at the differences that help us identify one or the other as the compound. Are you all good with those? Does anybody have any questions for me? Can we do 6 in this, on this page? Actually, even 5 looks good too. How about 6? By the way, what's the relationship between those 2 compounds and 6?
They're diastereomers, cis and trans.
6. Oh, okay, yes, you're absolutely right. Sorry, I wasn't looking carefully. They are absolutely diastereomers. They are cis and trans, absolutely. Okay, so how do we differentiate, use proton NMR to differentiate between the cis and the trans? Anybody? How many signals, proton signals, can we expect for this point? Sorry?
2.
Are you sure?
I was thinking like 1 signal.
One signal, no, not 1, but not 2.
What about
3.
3.
yeah?
Why 3?
Both sides and the top.
Both sides and the top.
Is it
What do you
because
mean
it's-
by that?
Wasn't there a plane of symmetry?
2
There is a plane of symmetry.
Yeah.
Actually, there's no plane of symmetry, there's a point of symmetry, which means plane means you can cut a molecule into, I can cut it into identical halves. That's plane of symmetry. A point of symmetry is you have this, and if you rotate it around that axis, that point, you'll get something symmetrical. So you're absolutely right, it has an axis of symmetry, also known as point of symmetry, right here in the center, that if I rotated the whole molecule about that, you would get this same, or something related, not this one, sorry, this guy has it. This guy has a plane of symmetry that has a point of symmetry. But yes, so it's meso, it's definitely meso because it has a plane of symmetry. It's definitely meso, which means it's achiral, does not have an enantiomer, but that doesn't mean anything in terms of NMR though. How many signals, proton signals, do we expect for the first one? Somebody said 3. I'm interested as to how. So what can you say about these 2? Are they equivalent or not equivalent?
Equivalent.
You all agree?
Yep.
Because yes, as you said, Dash, there is a plane of symmetry right there. I can cut it into 2 identical halves where this is equal to that. Absolutely right. Where are the other 2 then?
In,
the chlorines and the one above.
Say again?
Chlorines on the bottom.
I can't hear you.
The chlorines on the bottom.
The chlorines are on the bottom. Hydrogen, we're looking at hydrogen. It's proton NMR spectrum. There's a hydrogen here, and there's a hydrogen there, right?
Yep.
What's
Can-
the relationship? Sorry, Mark?
No, I was thinking they can be like that, right?
They can be.
Like this.
Oh, this is a different view of the molecule. So this is a different view of the
Oh,
molecule.
okay, okay.
Again, I was trying to make the model to show you.
Okay.
So in this view of the cyclopropane ring, it's up or down.
Yeah, up and
Yeah.
down.
Okay, but what's the relationship between that blue hydrogen and the red hydrogen?
They're
They're diastereotopic. They're not enantiotopic. They're not homotopic. These hydrogens are diastereotopic. How would you know? Okay, let's just look at the blue. When the blue that's pointed up, what does it see around itself? It sees hydrogen. Isn't that right? On the
Yeah.
same side of the ring. But what about the red? What does it see? It sees
chlorines.
chlorines.
Yeah.
They're in a diastereotopic environment. And what do we know about diastereotopic hydrogens?
One,
They
two.
are NMR
So they're NMR
inequivalent,
equivalent.
not equivalent, non-equivalent. They give different signals in NMR. So absolutely, this guy is expected to give 3 signals in NMR. What about this guy, which has a point of symmetry or axis of symmetry? How much? Sorry, what did you say? 2 signals only. Because both of these hydrogens are actually equivalent. They see the same things around them.
Yeah.
This guy sees hydrogen chlorine. This guy also sees hydrogen chlorine. Absolutely the same chemical environment, so they are equivalent in NMR.
Wait. Doesn't that hydrogen in red also sees the same stuff?
Does it?
Because
You got
there's a
to think
ClCl.
three-dimensionally, Iman. You got to see 3-dimensionally. If you have, let's say, I'm just going to use white for chlorines. So the chlorines are pointed downwards. Those are chlorines, right?
Yeah.
Yep.
So what does this hydrogen see around it?
Oh, it sees other carbon.
Chlorine is on the bottom
Oh, it
face.
sees carbon.
Hydrogen's on the
Oh, yeah.
top face. So it sees hydrogen, 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 right?
Yeah.
What about this one, the one I'm holding? Hydrogens are on the other side. It sees chlorines on the same side as itself.
Mhm.
So they are in different chemical environment. This is surrounded by hydrogen electron cloud, whereas this one is surrounded by chlorine's electron cloud.
Yeah.
So their chemical environments are different.
Mm.
That's not the case here though, because as we were saying earlier, it has an axis of symmetry, so they're
Mm.
equivalent. Does everybody understand that?
Much better now.
Everybody okay?
Yeah.
Cool?
Question,
Yes, Eric.
cycloside on splitting, the first one.
Okay, let's talk
So
about
there-
that.
Even though the two different B and C are different, have the same number of signal bonds from A
Yes,
or B. will they have
Absolutely.
Different,
the multiplicities will be the same.
okay.
Absolutely, you're
Alright.
absolutely right.
Just looking
B
at
is
it.
coupling with those two and itself. And this is coupling with these two and that.
But there's no difference in strength. Okay.
No, no difference in multiplicity, no difference in integration. The only difference is there are 3 signals here, there are 2 signals there. Exactly right. Absolutely. Everybody okay with that? Cool. Any questions? Is there any other one you want to work on here? Oh, 7 looks interesting. What do you guys think about 7?
I think that's
that's the $1 million question.
I was gonna ask.
What is D? Anybody know what is D?
deuterium.
It's deuterium. What is deuterium?
It's 2H. It's the 2H.
Which means what? It has 1 proton, 1 electron, and
1 neutron.
so it's an isotope of hydrogen, but this is not NMR active. This does not show up in NMR. So this nucleus of deuterium is not NMR active. For hydrogen, it's only the H isotope that shows in NMR. So basically, the point is we replace that hydrogen with deuterium, so that does not show in NMR. This does show in NMR. So how many signals would we get for this molecule?
One.
Careful.
2
One
signals?
signal?
2. I'm seeing 2 for this one.
Oh, wait, sorry, I was thinking.
The one with the hydrogen.
Oh, right.
How many signals? 2, 1 and 2, right?
Yep.
But then if I take that away and replace it with deuterium, what happens to this signal?
It becomes,
It's gone.
it's
Yeah.
just one signal.
Then all you see is those. H we can see in NMR, D we don't see in NMR.
Is
T
it kind
we
of like
don't see.
a spectator or not really?
Say that?
Spectator?
No, this has nothing to do with spectator ion. Those are for ionic compounds. These are covalent bonds. So no, this has nothing to do with spectator ions and all. The idea here is the nucleus of deuterium does not create different magnetic field levels for them to actually show in NMR. So only certain nuclei are NMR active, others are not NMR active. So yeah, that's, please, if you see D, very common for us to actually use deuterium to basically study specific things about a molecule. The idea is, does not show in NMR, shows in NMR. That's it. Everybody okay?
Yeah.
Okay, so what I want to do starting today is at least spend time actually looking at specific proton NMRs spectra and learn slowly, let's one at a time, learn to use those to figure out the structures of molecules. And this is just as a demo, this is more of an FII kind of a introduction to proton NMR spectra. So this is what proton spectra look like, NMR spectra. It's the engineers, they're breaking apart their engines and they do it right there.
Yep.
And I've talked to them before. It's more of it. Sorry, I'm digressing there. This is a typical appearance of a proton NMR spectrum. Please notice the baseline starts at 0, that's where TMS is. That's the reference we actually add to make that 0. And then you might notice a tiny blip right here around 7.24, which is the typical place where CdCl3 shows up. That's a solvent we use to dissolve our compound, deuterated chloroform, and it typically shows up around 7.24-ish kind of thing. So that little blip is the solvent, we don't need to worry about it. That TMS, we don't need to worry about that. So our compound has only 2 signals, 1 and 2. The first one is blown up here, we just zoomed in. The second one is zoomed in here. So there are 2 signals. If you look at this, that's the chemical formula of the compound, C2H5Br. So here's what I always do when I'm working with NMRs. First thing I do is I calculate IHD. Please, let's calculate the IHD for C2H5Br. Do you guys remember us doing that earlier in this chapter? Index of hydrogen deficiency. Let's go ahead and do that. What is the IHD for C2H5Br? So just to remind everybody, if there's a halogen, we modify the formula. Can somebody remind me what's the modified formula for C2H5Br?
C2H6.
C2H6, exactly. Just add a hydrogen for every halogen. What's the saturated formula with 2 carbon atoms?
C2H6.
So what is the IHD?
0.
Meaning what? What does that mean?
It's saturated?
It is saturated, meaning what? Absolutely, you're absolutely right. So what does that mean? That there is no pi bonds, right? Or no rings either in this molecule, because IHC is 0. Everybody okay? Okay, now number of signals. How many? So what does that tell us? What does that mean? If there are two signals, there are
Two types
two
of hydrogens.
types of
Two types of H's.
hydrogens in the molecule. We good?
Yep.
I'm just going to call this, oh, they do that. This is A, that's B, it's already labeled. So what is the next thing is integration. So if you're looking at integration ratios, what is the integration of A's to B? Now I have given you the integration for now, 2 and 3. That's the integration, 2 for A, 3 for B. So, let me write it here. 2 is to 3. Everybody with me? Now guys, can you tell me what's the total number of hydrogens in this molecule? 5, right?
5 hydrogens.
What is 2 plus 5? Oh, 2 plus 3.
5.
So therefore, is it okay, is it reasonable for me to assume therefore that this is 2 hydrogens and this is 3 hydrogens?
Yeah.
Reasonable? Now please think about it and tell me, which group has a carbon attached to 3 hydrogens? Right, but specifically speaking, if I have a carbon with 3 hydrogens, what group is that? It's a methyl group. Reasonable?
Yep.
What group will have 2 hydrogens? Obviously on carbons here because all we have are carbons. What would it be if it has only 2 hydrogens on it?
Methylene.
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 CH2. Make sense?
Methylene.
Right? Now please let's look at multiplicities. What is the multiplicity for signal A? How many peaks is it split into?
Can it be 3?
Is it split into 3 or is it split in A? A.
It's
Please
split
A.
into 4
Oh,
pieces.
my bad.
It's zoomed up right there. Zoomed to look at it more clearly.
It's split into
Notice it's split into 1:2:2:1 ratio.
4.
4. That signal is split into 4 parts. What do we call that?
Quartet.
A is a quartet. What about B? So what do we call that? A
Triplet.
triplet. So if A is a quartet, how many, and remember we said A is a CH2, right? So how many neighboring hydrogens does it have?
3.
Has 3 neighboring hydrogens. Agreed?
Oh yeah.
How about this? B is a triplet. How many neighboring hydrogens
2.
does it have?
2.
So, and I think I talked about this last class a little bit. When you see 2 signals, a quartet and a triplet split into a ratio of 2:3, what group must that be? 2 hydrogens, 3 hydrogens. What group is this if you take it together? Exactly. That's the only way possible for a CH3
Bromo.
integrating for 3 hydrogens, CH2 integrating for 2 hydrogens. That's going to be a triplet. This is going to be a quartet to exist. Isn't that right? Yes? Everybody okay?
Yes.
How many carbons have we used up?
2
All
carbons.
carbons gone.
Yep. All
How many
carbons.
hydrogens have we used up?
All of them.
5, all
Yep.
of them done. What's left?
Bromine.
So where does that go?
It goes to the right side of the.
That's the only open position left. So one at a time, one piece at a time, one piece at a time, one piece at a time, you start bringing the clues and putting them together. So this is basically a spectrum for bromoethane. Does that make sense?
Yep.
And they're moved from the usual positions because of the bromine.
Oh, yeah, exactly.
Okay.
Exactly. You're a very good point. I mean, look at the chemical shift for the CH2. I mean, we would have expected it to be here, but bromine is shift. And if you look at that NMR table that I gave you, with halogens, the chemical shifts increase. The protons go a little bit more downfield. Similarly, CH3, we would have expected it here if there was no electronegative or bulky group on it. Now it's shifted over there. Absolutely, the chemical shifts.